Hello, and welcome to the Sleep Science Space. If you enjoy drifting off while imagining stars, planets, and the serene vastness of space, you're in the perfect spot. Tonight, we'll leave our familiar solar system behind and float into the dark stretches between stars where distant worlds orbit alien suns and the possibilities are endless. We'll explore planets where metal falls like rain, worlds sculpted by ice and fire, and massive lonely giants wandering the void without a sun. Some of this may seem impossible, yet every fact is real. If you like these calming journeys, feel free to like and subscribe. It helps others discover this space too. But for now, settle in. Let your body relax, let your mind drift, and let's begin. There are planets hotter than some stars. We often think stars are the ultimate furnaces, glowing with plasma and reaching millions of degrees. Surprisingly, certain planets come astonishingly close. Take Kelt 9b, for example. It reaches over 7,000 degrees F hotter than many red dwarf stars. This gas giant hugs its massive blue star so tightly that a year lasts just over a single Earth day. Locked tidally, one side faces its star, constantly enduring unceasing waves of radiation. Its atmosphere is being ripped away, streaming outward like a comet's tail. Heat here is so extreme that molecules break apart and metals vaporize. It's not merely hot, it is intense beyond imagination. These ultra hot Jupiters challenge our ideas of what a planet can be, blurring the line between planet and star with blazing infernos appearing briefly before fading into the darkness. Some planets might be almost entirely diamond. It sounds like science fiction, but under certain conditions, it could happen. Exoplanets rich in carbon may form with interiors that generate diamond like structures. If a planet develops around a star where carbon outnumbers oxygen, these materials can dominate its makeup. One example, 55 Cancri, a super Earth, twice the size of our planet, may harbor vast amounts of carbon under extreme pressures, potentially forming crystalline diamond deep within. It wouldn't sparkle like jewelry, only dense, dark, and unimaginably hard. Yet the concept is mesmerizing, a world shaped from carbon, where mountains may hide buried crystal, creating geology both alien and precious. Some planets orbit two suns, much like Tatooine in Star Wars. In fiction, twin sunsets have long captured our imagination, and now we know such skies may actually exist. Certain exoplanets, called circumbinary planets, circle not one, but two stars, tracing intricate paths around stellar pairs that themselves orbit each other. When the stars are close together, the planet can orbit them both as though they were a single luminous body. But if the stars are farther apart, the planet may orbit only one, subtly pulled and tilted by the distant gravity of the other. The result is a world with unusual day night cycles, shifting seasons, and dual shadows. These configurations are rare and fragile, yet they do exist. On such a distant planet, the sky could truly witness two dawns and two dusks, a scene once imagined in fiction, now quietly confirmed by science. Some planets experience rain unlike anything on Earth. Take HD 1189733b, a gas giant larger than Jupiter orbiting extremely close to its star, completing a year in just over 2 Earth days. Its atmosphere blazes at roughly 1,700 F, while winds raise across the surface at thousands of miles per hour. Tiny particles of silicate, the very material that forms glass, float in its blue, hazy skies. Under the right conditions, these particles condense and plummet as molten glass whipped sideways by ferocious winds. From afar, this world may appear eerily Earth-like, with a soft blue glow near its sun. Up close, however, it is a storm-racked furnace, terrifyingly beautiful and entirely uninhabitable. It is a vivid reminder that nature's creativity stretches far beyond our imagination. Some exoplanets are vast, deep oceans. Imagine worlds almost completely submerged in water, with no continents or islands, just endless global seas. Unlike Earth, where oceans are shallow by comparison, these planets could harbor water layers hundreds or even thousands of miles deep. Surface conditions might be calm wind-blown or violently stormy, but deep beneath pressures soar to unimaginable extremes. They're exotic forms of ice far denser than what we know form under crushing weight. At their centers, hidden beneath all that water, these planets may still harbor its rocky cores, silent anchors beneath the immense seas. Some of these planets may even harbor deep liquid layers warmed by internal heat. Could life survive in such alien oceans? The answer is still unknown. Yet ocean worlds could be far more common than we once imagined. Glistening silent planets with no land in sight, slowly rotating in darkness, far from any familiar sun. Not all planets spin like Earth. Some are tidally locked with one hemisphere, perpetually facing their star, while the opposite side remains shrouded in eternal night, the same phenomenon seen with our moon, which always shows us one face. Imagine this on a planetary scale, one half scorched by relentless daylight, the other trapped in endless darkness. Between them exists a narrow twilight zone, a ring around the planet where temperatures might be just right and light is low but steady. In some cases, scientists speculate that this delicate band could harbor life. These worlds may be battered by violent winds, shaped by strange cloud patterns, and dominated by extreme weather, yet they are real challenging everything we thought about habitability. Life. If it exists, there would have to adapt, perhaps living in the shadows or clinging to the edges of the light. Then there are the hot Jupiter's giant gas planets, skimming perilously close to their stars. Picture a massive planet, like Jupiter moved so near its sun that one orbit lasts only a few days, and surface temperatures soar past 2,000 degrees. At such proximity, the upper atmosphere is stripped away, streaming into space like a comet's tail. These enormous, tightly orbiting worlds were among the first exoplanets we discovered, their immense size and short orbital periods making them easier to detect. Yet their nature remains puzzling. How did such colossal planets arrive so close to their stars? Did they form there, or were they slowly nudged inward by gravitational forces over millions of years? Some trail luminous clouds of escaping gas, while others gradually shrink as their atmospheres evaporate. These worlds are volatile, dramatic, and often short lived, fleeting flashes of planetary fire tracing orbits around distant suns. Some exoplanets are darker than charcoal. Unlike Earth, not all planets reflect light. Certain worlds absorb nearly everything that hits them, becoming darker than paint ash or even the deepest charcoal. One striking example is Tries 2b, a gas giant orbiting a star about 700 light years away. Its atmosphere reflects less than 1% of incoming light. Scientists aren't entirely sure why. It might be due to vaporized alkali metals or mysterious chemical compounds high in the atmosphere. Whatever the cause, the effect is mesmerizing a planet as dark as coal, glowing faintly from internal heat, nearly invisible against the glare of its star. Even its night side, already shrouded in darkness, is only slightly cooler than the day. If you could stand nearby, you'd likely see only a faint silhouette, a perfect shadow drifting in silence, absorbing the light of the universe. We've also discovered planets wandering alone without a star. Most planets orbit suns, but some are rogue planets, drifting freely through space, unbound by any light. Evidence points to dozens, possibly hundreds, scattered across the galaxy. Some may have formed in normal star systems and been ejected by gravitational forces. Others might have formed in isolation, like failed stars never massive enough to ignite. These rogue worlds are dark cold and extraordinarily difficult to detect. Powerful infrared telescopes reveal their faint thermal glow. Some may retain internal heat, maintaining subsurface oceans for billions of years. Others drift frozen and silent worlds with no sunrise, no sky, and no warmth. Yet, even here, a quiet question lingers: could life exist in such stillness? Some exoplanets may have clouds of ruby and sapphire. When we picture clouds, we imagine soft, pale water vapor. But on scorching gas giants, where temperatures exceed 2,000 degrees, minerals that are solid on Earth rise and condense into clouds. Aluminum oxide iron, titanium, and in some cases corundum, the mineral form of rubies and sapphires, float high in the atmosphere. These mineral clouds scatter light in surreal ways, painting skies red purple or deep blue. On one planet, PAT 7b scientists have observed shifting atmospheric patterns, suggesting high altitude mineral clouds sweeping across the sky, a dazzling alien spectacle far beyond earthly imagination. It's hard to imagine a world wrapped in heat and storms lit by a blazing sun, with clouds of liquid gems swirling overhead. The universe is far stranger and more beautiful than we can easily picture. Some exoplanets fall into a category called super-Earths, rocky worlds larger than Earth, but smaller than Neptune. These planets may have stronger gravity, thicker atmospheres, and more stable climates. Some might even be more hospitable to life than our own world. One candidate is Kerr 442b, a rocky planet in the habitable zone of its star. Not too hot, not too cold, receiving just the right amount of sunlight. It has the mass needed to hold onto an atmosphere and liquid water. Some super Earths could host deeper oceans, fewer tectonic disruptions, and a steadier surface conditions that might allow life to emerge and endure. While we don't yet know if any of these planets are truly habitable, they remind us that Earth is not necessarily perfect, just the one we call home. Some planets orbit their stars in just a few hours. Most planets take months or years to complete an orbit. Earth takes 1 year, Mercury 88 days. But certain exoplanets move astonishingly fast. Kepler 78b, slightly larger than Earth, completes a full orbit every 8.5 hours. It lies so close to its star that its surface is likely molten rock, with temperatures reaching thousands of degrees. These ultra short period planets are often tidally locked, their days and nights frozen in place, stars looming enormous in their skies. Gravity strains their structures, and some may even be slowly tearing apart. Extreme, fast, hot, and fleeting, they exist skimming the edges of their stars like sparks flying from a flame. Other planets move at the opposite extreme, taking centuries to orbit their stars. One of the slowest discovered is Goopisium b, a gas giant with an orbit lasting roughly 1,000 years. It drifts so far from its star that it's barely held by gravity. Any farther, and it might escape entirely. These long period planets are incredibly difficult to detect. We cannot wait 1,000 years to watch a single orbit. Instead, astronomers catch them in motion, glimpsing a curved path, a faint arc, a hint of vastness. Some may have cold, dark surfaces, illuminated only by faint starlight. Others might experience seasons that span generations. On such worlds, change is measured not in years, but in lifetimes, a slow and silent rhythm far beyond our own. We have now discovered the thousands of planets beyond our solar system. For most of human history, we knew only our own planetary neighborhood, the sun, the moon, and the wandering stars crossing the sky. But everything changed in the 1990s when the first exoplanets were confirmed, opening our eyes to a universe teeming with possibilities. Now, thanks to space telescopes like Kepler and TESS, we've discovered thousands of planets orbiting distant suns. Some are small, rocky, and Earth-like, while others are massive and strange. Some race tightly around their stars in just a few days. Others take centuries to complete a single orbit. Each discovery reshapes our understanding of what's possible, and yet this is only the beginning. Astronomers estimate there are hundreds of billions of planets in our galaxy alone, more planets than stars. Worlds upon worlds quietly circling in the darkness. We may never reach most of them, but we can listen for them measure the shadows they cast and wonder what mysteries await out there. Many planets have been detected through the shadows they cast during transits. Normally, a star's light is steady, but sometimes, just briefly, it dims a tiny dip, a momentary flicker. That dimming can mean a planet has passed in front of it. This is called the transit method, one of the most powerful tools for finding exoplanets. When a planet crosses its star from our perspective, it casts a faint shadow, not in the dramatic way of eclipses, but in subtle drops in brightness, often less than 1%. Telescopes like Kepler and TESS have used this technique to find the thousands of exoplanets. From those tiny shadows, we can learn the planet's size, its orbit, and even hints about its atmosphere. We watch stars blink ever so slightly to reveal unseen worlds, the light of a distant sun interrupted by the quiet silhouette of a planet far away. Others have been found by the gravitational wobble they induce. Even a planet's gravity leaves a fingerprint. As a planet orbits a star, it nudges the star slightly, causing it to wobble. That motion is tiny but real. As the star shifts, its light stretches and compresses. Astronomers detect those changes through spectroscopy, breaking starlight into its components and searching for subtle signatures of motion. This radial velocity method was how the first exoplanets were discovered. It works best for massive planets close to their stars, like hot Jupiters, but it has also revealed multi planet systems and long period orbits. We are not seeing the planets directly. Instead, we watch their stars sway under their pull, a distant dance we cannot see but can feel in the rhythm of the light. Some exoplanets appear to have atmospheres slowly escaping into space. A planet's atmosphere is never truly still. Winds blow clouds, drift, particles escape. But in some extreme cases, the entire upper atmosphere may drift away, leaking into space like breath into the void. This is especially common among hot, close in gas giants, where intense stellar radiation heats the outer layers until they reach escape velocity. These planets can develop long, comet like tails of escaping hydrogen and helium. We've observed this in several exoplanets, where ultraviolet light reveals streams of gas trailing behind them. Some may lose significant mass over time, while others might be stripped down to their rocky cores. This process shapes the evolution of planetary systems, showing how stars can sculpt, reshape, or even destroy their planets. It's a vivid reminder that even worlds can change, erode, and fade, leaving only gravity in their wake. We've discovered planets and star systems with three or more suns. Not every star system resembles our own. Some contain two, three, or even more stars orbiting each other. In a few of these complex systems, planets exist. Imagine a world where the sky is never truly dark, where shadows stretch in different directions. One sun rising while another sets. These planets must follow delicate, stable paths to survive the tangled gravitational pull of multiple stars. Some orbit closely around a pair of suns, circumbinary planets, while others orbit far beyond the cluster, tracing wide arcs around a chaotic center. The lighting would be strange, the seasons unpredictable, and the sky full of motion. Yet these planets persist, reminding us that planetary systems can form in ways we never expected, even in places where gravity is complicated. The night sky never settles. Planets always find a way. Some worlds orbit the collapsed remnants of dead stars. Stars do not live forever. Some end their lives as white dwarfs, dense remnants of stars like our sun. Others collapse into neutron stars or black holes. Around some of these stellar corpses, planets endure. These worlds orbit what remains after a star has died, glowing embers or pulsing remnants of stellar fury. Some have survived the chaos of a supernova, while others may have formed from debris left behind, rising from ashes into something new. The light from these stars is dim, cold, or distorted, yet the planets remain tracing silent paths through a stellar graveyard. Some are blasted by radiation, while others drift quietly circling dead suns in eternal twilight. It's haunting and beautiful, a reminder that even after an end, something new and strange can begin. And then there's a planet that orbits its star backwards. Most planets follow the spin of their star, forming naturally from a swirling disk of gas and dust. But nature does not always follow the rules. At least one exoplanet, WASP 17b, defies expectation, orbiting in the opposite direction of its star's rotation. Instead of moving with the star's rotation, it pushes against it. This backwards orbit likely formed through chaos, a near collision, a gravitational shove, or some violent rearrangement long ago. WASP 17b is massive, bloated, and blisteringly hot, orbiting close to its star every few days. Its reverse motion challenges our understanding of planetary system evolution and proves something remarkable. The universe is more flexible, chaotic, and surprising than any single theory can capture. Some planets follow the flow, others push against it, and a few, like this one, drift through the cosmos with quiet defiance. We've seen signs of clouds on planets light years away. It may seem impossible, but astronomers have detected clouds on exoplanets dozens, even hundreds of light years from Earth. Not by seeing them directly, but by analyzing starlight as it filters through a planet's atmosphere during transit. Some wavelengths are absorbed, others scatter or pass through, leaving a delicate fingerprint that reveals gases, molecules, and particles suspended in the air. In several cases, this data hints at clouds, dark metallic or mineral based, made of silicate iron or other exotic compounds. These clouds can reflect or block starlight, shaping the planet's appearance and surface temperature. Some worlds are permanently shrouded, while others show shifting patterns across their skies. Though we cannot see them directly, we can read their weather from starlight alone. Some exoplanets orbit even closer to their stars than Mercury. Mercury is already scorching the closest planet to our sun, stripped bare by its heat. Yet some planets circle their stars at distances far closer than anything in our solar system, completing orbits in mere hours or days. Their surfaces may be molten atmospheres stripped by stellar winds, and many are tidally locked, one side blistering in unending daylight, the other frozen in eternal night. Others bulge under tidal forces, stretched like teardrops by their star's gravity. These extreme worlds challenge our notions of habitability, yet they are often among the easiest to detect thanks to their short orbital periods. Many of the first exoplanets discovered fell into this category. Hot, extreme, and sometimes unstable, they show just how flexible and dynamic planetary systems can be. Others drift far beyond the reach of any sunlight. Not all planets cling to their stars. Some orbit so distantly that sunlight is only a faint, feeble glow. These distant worlds may take hundreds or even thousands of years to complete a single orbit. Temperatures plummet. Seasons span generations, and in the deepest cold chemical reactions may slow to a crawl. Yet even here, Planets persist silent and slow, circling their stars at the very edges of gravity's reach. Some may be icy giants wrapped in frozen clouds. Others could be rocky and barren, crusted with ice and carbon dust. Some may harbor hidden warmth beneath the surface, sustained by radioactive decay or ancient heat trapped from formation. These far flung orbits are difficult to detect, but their existence reminds us that planets can survive in places we once thought empty. Even in the loneliest reaches of space, a world can quietly endure. There are planets with spectacular, hypothetical ring systems. Saturn's rings are beautiful, delicate bands of ice and dust circling a gas giant. But they may not be the grandest in the universe. Some exoplanets appear to have rings thousands of times larger, stretching across vast distances wide enough to eclipse their host stars. One candidate is J1407b, a giant planet or brown dwarf that may be surrounded by a ring system over 200 times larger than Saturn's. These rings could be made of ice rock or dust, possibly the remnants of forming moons. As the planet orbits, its rings may cast deep shadows on the star, creating strange dips in light detectable from Earth. If such a planet were placed in our solar system, its rings would stretch across the night sky. For now, they are hypothetical, but their shadowy presence hints at the grandeur still waiting to be confirmed. We've only just begun to scratch the surface. For all we've learned about exoplanets, we're still at the very beginning. The first confirmed discovery was made in 1992. In cosmic terms, that's barely a heartbeat ago. Since then, technology has leapt forward. Thousands of planets have been found, and thousands more await confirmation. We've detected atmospheres, measured sizes and orbits, and mapped their skies in light and shadow. Yet we've barely begun to understand what these worlds are truly like. We cannot yet see their surfaces. We don't know what they smell like, sound like, or feel like underfoot. We can't say which have clouds, continents, or even creatures. Every new exoplanet is a doorway to something we've never seen. And as our tools grow sharper, the picture will only grow stranger, richer, and more wondrous. The cosmos is full of secrets, and we've only just knocked on the door. Some planets orbit so close they are slowly being vaporized. For these worlds, proximity to a star is more than hot, it's destructive. Intense radiation and stellar winds strip away their outer layers. Atmospheres heat expand and gradually evaporate into space. Some form long glowing tails of gas that stretch behind them like comets caught in eternal retreat. Over time, these planets lose mass, slowly shrinking, thinning, or transforming entirely. One planet, KIC 1255754-8b, may be crumbling under this kind of erosion. Its surface sheds dust and debris with every orbit. It's like watching a planet dissolve in slow motion. These aren't just places to exist. They are dynamic systems constantly reshaped by their environment. Even something as vast as a planet can be worn away little by little by the unrelenting light of a star. We've discovered worlds that defy all expectations. Every time we think we understand planets, the universe hands us something we can't explain. We've found planets where the skies shimmer with vaporized metal. We've seen rocky worlds hotter than lava, and giant gas planets colder than deep space. Worlds with tilted orbits, backward spins, and rings so large they could block out a star. Some planets are too dense, others are too fluffy, some shouldn't exist at all, at least not according to our models. But they do. Each strange discovery forces us to rethink how planets form, how they evolve, and what might be possible. Science thrives on these surprises. In the chaos of the cosmos, order is only part of the story. The rest is made of exceptions, edge cases, and quiet contradictions. Little cosmic puzzles scattered through space, waiting for someone to notice and wonder. Some exoplanets might be water worlds with no land at all. Imagine a planet with no continents, no islands, no shorelines, just endless ocean stretching in every direction. These are water worlds, exoplanets, where the surface may be completely covered by liquid water. Not shallow seas like Earth's, but oceans hundreds or even thousands of miles deep. Beneath the surface, the pressure would be intense enough to compress water into exotic ices and crush rock into unfamiliar forms. Some of these worlds might have atmospheres rich in steam or clouds of vapor circling overhead. Others could be wrapped in hazy mists, warmed by sunlight or internal heat. If life exists on these planets, it would evolve in a deep, sunless sea, shaped by currents and chemistry rather than light. We haven't confirmed one yet, but the evidence is growing. And if Earth is one kind of habitable world, then perhaps these dark oceans are another kind entirely. We've found many Neptunes small, but swollen with gas. Not every planet fits neatly into the categories we know. Between Earth and Neptune lies a curious group called mini Neptunes. They're bigger than Earth, but smaller than our ice giants, and many are wrapped in thick layers of gas. These planets likely have rocky or icy cores surrounded by envelopes of hydrogen, helium, and other gases. They may look similar to Neptune from a distance, but inside they could be wildly different. Some may have deep boiling oceans beneath their clouds. Others might have no solid surface at all. They're too small to be true gas giants, but too big to be rocky super Earths. For a long time, we didn't even know if planets like this could exist. Now, we know they're common, possibly the most common type of planet in the galaxy. Strange, swollen, and still mysterious, they fill in the space between what we expected. Some planets are puffed up like balloons. Some exoplanets are so inflated they seem lighter than they should be. These puffy planets are large in size, but low in density, huge soft worlds that could float in water if they were somehow dropped into a bathtub the size of a star. One example is WASP 17b, a gas giant twice the size of Jupiter, but with only a fraction of its mass. These planets likely formed far from their stars, then migrated inward. Now, intense heat from the star causes their atmospheres to swell and expand. Radiation from the star may be breaking apart molecules, adding to the planet's strange properties. Some puffy planets have visible tails of escaping gas. Others seem impossibly light for their size. We still don't fully understand them, but they show how elastic a planet can be, not rigid and fixed, but soft, unstable, and stretched by light. There are exoplanets with days longer than their years. On Earth, 1 day and 1 year are very different things. We spin on our axis once every 24 hours, but it takes 365 days to orbit the Sun. Not so for some exoplanets. In certain cases, especially for planets orbiting very close to their stars, the time it takes to rotate is longer than the time it takes to complete an orbit. That means the planet completes a full loop around its star before it even finishes turning once. These planets are usually tidally locked with one side permanently facing their sun. The night side remains in darkness, frozen and still, while the day side burns under endless daylight. There's no sunrise or sunset, just one eternal face to the light. On such a world, the idea of time itself begins to blur. A day that never ends, a year that races by a sky divided forever in two. Some worlds may be covered in thick, hazy skies. We often imagine alien worlds with clear skies and stunning views, but some exoplanets might be wrapped in thick layers of haze, blocking the light and obscuring everything below. These hazes can be made of complex hydrocarbons, photochemical smog, or exotic clouds of unfamiliar chemistry. On Earth, we see this kind of effect on Saturn's moon Titan, where a golden fog hides the surface from view. On exoplanets, especially, those orbiting cooler stars, ultraviolet light can trigger strange reactions in the upper atmosphere, building up thick, murky layers that trap heat and scatter light. These planets may look dull or muted from space, their colors softened by haze. But beneath the clouds, oceans might churn, winds might scream, and alien landscapes may wait in silence. We can't see them clearly, not yet, but we know the haze is there, a veil drawn over distant hidden worlds. We've seen evidence of winds whipping at thousands of miles per hour. Weather doesn't just happen on Earth. On many exoplanets, especially large gas giants, atmospheric winds can reach extraordinary speeds far beyond anything seen in our solar system. Some exoplanets are tidally locked with one side, always facing their star. That intense permanent heat creates powerful thermal gradients that drive fierce winds around the planet's atmosphere. Using space telescopes, astronomers have detected signs of winds blowing at up to 5,000 miles per hour, fast enough to travel the width of the United States in under an hour. These winds can shift clouds, reshape heat patterns, and carry vaporized metals across the planet. Some even redistribute light itself, shifting the brightest part of the planet away from where the star's light hits directly. It's invisible to the eye, but written into the glow of the planet's light, a whisper of motion in a faraway sky. Some planets could be tidally heated from the inside. Not all heat comes from a star. Some exoplanets, especially those in eccentric orbits, may be heated from the inside out, thanks to tidal forces. As they move through varying gravitational pulls, their interiors stretch and flex, creating friction and warmth deep below the surface. This is how Jupiter's moon Io stays volcanic, and how some exoplanets do too. Planets orbiting close to large stars or engaging in gravitational dances with neighboring planets can experience this kind of tidal heating. In some cases, it could melt rock into magma or keep subsurface oceans liquid beneath thick shells of ice. These planets might look cold or dark on the outside, but inside they're alive with motion, heat without sunlight, activity without a star. It's a reminder that energy can come from within, and that even in the outer reaches of a system, a planet may still be warm. We've discovered planets in ancient star systems. Some stars are nearly as old as the universe itself, formed in the galaxy's earliest chapters. And around a few of these ancient stars, we've found planets. They've been orbiting for billions of years, far longer than Earth has existed. One example is KA 444, a star system over 11 billion years old with five small rocky planets. These worlds are from a time when the universe had fewer heavy elements, suggesting they may have formed from different materials than Earth. What might such planets be like? Could they be worn smooth by eons of impacts? Could they have once supported life long before life began here? We may never know, but these ancient systems remind us how long planets can last, surviving stellar storms, galactic tides, and the slow march of time. They are cosmic elders quietly circling in the deep past. Still here, still turning. Some exoplanets may have moons we've yet to find. Where there are planets, there may also be moons. And yet, for all the exoplanets we've discovered, exomoons, moons orbiting planets outside our solar system remain elusive. They're hard to detect, small, subtle, often hidden in the noise. But we've seen hints, tiny variations in a planet's transit wobbles, in timing dips in brightness that don't quite match the model. One candidate, a possible moon orbiting the gas giant Kepler 1625b, is still under study. If confirmed, it would be huge, larger than any moon in our solar system. But even smaller exomoons could be important. They might stabilize planetary climates, shape tides, or even provide sheltered environments for life. Some moons could have subsurface oceans, like Europa or Enceladus. Some worlds skirt the very edge of what we consider habitable. This region, often called the Goldilocks zone, is where temperatures could allow liquid water to exist. But even within this just right space, conditions can vary wildly. One planet may have scorching days and freezing nights, while another could be cloaked in thick clouds that trap heat or obscure the surface entirely. Planets in these zones might host environments beyond our imagination. Some could harbor oceans beneath icy shells warmed by the planet's own heat rather than sunlight. Others may have atmospheres dense with exotic gases, shifting constantly under alien weather patterns. Life, if it exists, may thrive in forms utterly unlike anything on Earth. Microbial colonies, chemical networks, or self replicating systems adapted to extreme pressure, acidity, or darkness. Even planets on the fringe of habitability reveal the incredible diversity of the cosmos. Some orbit so close to their stars that one side bakes endlessly while the other freezes in permanent night. Others drift so far away that sunlight barely reaches them. Yet internal heat from radioactive decay or tidal forces might keep their cores alive and active. And then there are worlds that defy classification entirely. Massive objects on the borderline between planet and star, brown dwarfs or super Jupiters, glow faintly from leftover formation heat. Some may even fuse small amounts of deuterium in their cores, teasing the boundary of what it means to be a star. These objects remind us that space rarely conforms to strict categories. It's a spectrum, a continuum, a universe full of gradations where boundaries shimmer and shift. In every corner of the galaxy, planets challenge our expectations. From frozen giants and tidal heated worlds to cloud shrouded mini Neptunes and distant rogue planets, the universe continuously expands what we thought was possible. Each discovery is a glimpse into a reality both stranger and more wondrous than we can easily imagine. Many exoplanets hover right on the edge of the habitable zone, where conditions are uncertain and changeable. Too far from their star, and water freezes solid. Too close, and it evaporates completely. But along this delicate boundary, other factors come into play. Thick atmospheres can trap heat, reflective clouds can cool a surface, and eccentric orbits or seasonal shifts can create extreme swings in temperature. On some worlds, one hemisphere may support life, while the other remains inhospitable. Microbial life might survive only in hidden pockets beneath ice in deep caves or near geothermal vents. These planets exist in a precarious balance where warmth and cold, light and dark dance at the edge of possibility. Thanks to advanced instruments like the James Webb Space Telescope, scientists are beginning to study the atmospheres of these distant worlds. As a planet transits, its starlight filters through the gases above its surface. That light carries tiny signatures, spectral lines from molecules in the air. By analyzing these lines, astronomers can detect water vapor, methane, carbon dioxide, and hints of clouds or pressure. In rare cases, they might even glimpse signs of life's subtle chemical fingerprints that suggest biological activity. Each spectrum is a whisper from across the galaxy revealing the hidden character of alien skies. Some exoplanets experience seasons unlike anything on Earth. A dramatic tilt, elongated orbit, or multiple stars can create decades long summers or centuries long winters. One orbit might bring a planet scorching close to its sun, only to drift it far into icy darkness. Others have chaotic, unpredictable cycles. Life, if present, would not follow a familiar calendar of days or years, but a rhythm set by slow arcs and stellar choreography. Entire generations could rise and fall within a single season, attuned to a cycle far slower and stranger than our own. On these distant worlds, time itself may feel different, and the cycles of day and night can be unlike anything on Earth. Some planets exist in a state of eternal twilight. These are often tidally locked with one side forever facing their star, while the opposite remains in permanent darkness. Between these extremes lies the terminator, a narrow band of perpetual dusk. Here, the sky may hold a constant soft glow, winds are gentler, and temperatures more stable. If life exists, it might cling to this delicate boundary, flourishing in muted light and quiet shadows. No sunrises or sunsets occur, only the steady, slanted light of a star suspended along the horizon, a place where time drifts in half light and the world never fully sleeps. Some planetary systems display remarkable synchrony. In certain cases, planets orbit in resonance, their motions linked in precise ratios. One planet might complete two orbits, while another completes three. These orbital resonances prevent collisions and maintain stability over millions of years. Chains of resonance have been discovered with three, four, or more planets, creating a cosmic rhythm akin to a celestial symphony. Each world follows its own beat, yet together they remain in harmony. The arrangements are delicate. A small disturbance could disrupt them entirely, yet they persist orbit after orbit, a quiet testament to the universe's subtle music. Other exoplanets present mysteries we have yet to fully understand. Some display irregular light curves, dimming and brightening in ways that defy simple explanations. Rings, clouds, or orbiting debris may create unusual shadows. One famous example, Tabby's star, exhibited strange, uneven dips in brightness. While comets or dust clouds might explain some behavior, the full cause remains unknown. Transit patterns wiggle and shift. Some planets show unexpected dips before or after crossing their star, and others seem shrouded in clouds or trailing dust. These faint flickers are puzzles, tantalizing signals from worlds far away reminding us how much remains hidden. Some exoplanets follow wild, elongated orbits that almost fling them from their stars. Unlike regular circular paths, these extreme trajectories can stretch for hundreds of years. At the farthest point, the planet may endure near total darkness and freezing cold. As it swings back, it plunges past its star heated rapidly by intense radiation and gravity. These orbits are unstable, often temporary, and sometimes caused by collisions or the gravitational influence of passing stars. They are violent, dramatic journeys, a reminder that planetary systems are not always calm, predictable places. Some planets may one day drift free, escaping the pull of their stars to wander alone through interstellar space. They are cosmic exiles, barely tethered, tracing unpredictable paths through the darkness. Their futures are uncertain, yet they continue to move, a reminder of how dynamic and fragile planetary life can be. Other exoplanets orbit the remnants of dead stars, such as white dwarfs. When a star like our Sun reaches the end of its life, it sheds its outer layers and collapses into a dense, hot ember. Though these stars no longer fuse hydrogen, they remain luminous for billions of years. Around some of them, planets endure. Some survived the star's violent expansion into a red giant. Others may have formed later from leftover debris. The environment is extreme, crushing gravity, lingering radiation, and intense heat. Yet these worlds persist. Some even occupy narrow zones where liquid water could exist. They orbit the dead yet remain alive survivors in a universe of change. Planets can also rise from destruction. Young star systems are chaotic, with collisions shattering planets, ripping apart moons, and scattering debris across space. From this cosmic wreckage, new worlds can emerge. Dusty disks around stars show ring like gaps hinting at collisions and rebuilding. Some exoplanets may be stripped cores of once larger planets. Others could be assemblages of fragments fused by gravity over time. These recycled planets may have scarred molten surfaces and unusual orbits, but they endure. Destruction here does not mark the end. It can be the beginning of something stranger, tougher, and more resilient. Some planets may not even belong to the stars they orbit. Over billions of years, gravitational interactions can fling planets from one system into another. A planet might start life around one star and end up captured by another, moving along tilted or eccentric orbits. Their chemical signatures or motion sometimes reveal this wandering history. These interstellar travelers are cosmic immigrants, reminders that solar systems are not isolated. They evolve exchange members and sometimes adopt strangers from across the galaxy. Finally, some exoplanets may be young echoes of Earth itself. Observing them is like glimpsing our planet's distant past, thick carbon dioxide atmospheres, methane rich skies, and nascent life just beginning to emerge. Continents may still be forming volcanoes, shaping the surface and oceans slowly collecting. These early Earth analogs offer a window into how planets and life take shape over billions of years, showing us that the story of worlds is as ancient as it is ongoing. Studying these distant worlds can give us clues about Earth's own past. What did our skies look like? Billions of years ago, which gases filled the atmosphere? What storms swept across silent oceans? Some exoplanets may serve as frozen snapshots of an earlier chapter in planetary history, distant echoes of Earth before life emerged to witness it. Not all stars are bright or massive. In fact, the majority in our galaxy are small, dim, and long lived red dwarfs. Yet around some of these modest stars, we've discovered planets as large as Jupiter. At first, it seems improbable, a tiny star hosting a colossal world, but nature often surprises us. Many of these giants orbit extremely close to their stars, completing revolutions in just a few days. The contrast is dramatic, enormous planets looming beside faint ember like suns. These pairings challenge our old assumptions about planet formation and show that even diminutive stars can host striking dynamic planetary systems. Planetary systems also vary widely in scale. While our solar system has 8 planets, some stars host dozens of worlds. Observations from Kepler and TESS have revealed compact systems with 5, 6, or even 7 confirmed planets, with hints of more waiting to be found. In these systems, planets orbit very close to their stars, closer than Mercury is to the Sun. On one of these worlds, another planet might appear as a bright disk in the sky, not a star, but a nearby neighbor. Often their orbits are locked in delicate resonances, moving in coordinated rhythms like gears in a cosmic machine. Such systems expand our understanding of how planets can arrange themselves, forming configurations radically different from our own. At the other extreme, some stars host only a single known planet. Whether these solitary worlds formed alone, lost siblings, or simply elude detection remains uncertain. What we do know is that they traverse their orbits in silence, untouched by the gravitational pull of nearby companions. Each system, whether densely packed or utterly isolated, reminds us that planetary architecture is as varied and unpredictable as the stars themselves. These solitary planets may have histories as calm as the void or as tumultuous as the storms that once shaped them. Some drift slowly in wide orbits as massive gas giants, while others cling tightly to their stars, small, rocky, and scorched. Standing on one of these lonely worlds, or imagining it, the sky would feel immense and empty. No nearby neighbors rising like moons, no orbital dances shaping the climate, just a single planet, a single sun, and a quiet rhythm in the vast darkness. Some exoplanets are veiled in thick rolling steam. Picture a world where oceans boil into dense clouds of vapor, wrapping the surface in haze. These steam worlds often orbit close to their stars, where surface water cannot remain liquid. The atmosphere becomes a turbulent, glowing shroud, and below the fog, liquid water, or even solid ground, might persist hidden from view. Sky and sea merge into one, creating a planet in transition where boundaries blur and the surface is lost in vapor. On other worlds, ice can behave more like rock than water. In extreme cold or under immense pressure, water crystallizes into exotic high pressure ices such as Ice 7 or Ice X. Beneath thick oceans or frozen crusts of icy super Earths, these solid layers may flow slowly or remain motionless for eons. Mountains of ice could rise unmelted while hidden oceans churn beneath, kept warm by internal heat trapped deep within. Exotic ices don't stop at water. On planets in the far reaches of their systems, ammonia, methane, or nitrogen may freeze, forming colorful frost in shades of pale blue, pink, or yellow. These frosts can build jagged ridges, smooth plains, or glittering surfaces under a distant faint sun. Some might sublimate into thin atmospheres, while others endure for billions of years. These frozen worlds, massive and silent, resemble Pluto or Neptune's moons, but on a grander scale where chemistry sculpts the landscape. The air is thin, the light dim, yet in their quiet, icy expanse, these planets are some of the galaxy's oldest and most enduring travelers. We've found planets forming in the very cradles of stars. Most stars ignite within crowded clusters, vast nurseries containing hundreds or even thousands of young suns. For a long time, scientists wondered if planets could survive in such chaotic neighborhoods. Gravity tugs, unpredictably, radiation blazes, and close encounters with neighboring stars could easily disrupt nascent worlds. Yet planets do exist here. Some of these exoplanets orbit, while dozens of other stars blaze around them, bathing their skies in ultraviolet light, far brighter than anything on Earth. Some form quickly clinging tightly to their young stars. Others struggle to hold onto tenuous atmospheres or are flung from their birth systems, becoming rogue wanderers. Still, some remain resilient and spinning through their crowded stellar nurseries. The view from these worlds would be spectacular, an endless sea of brilliant stars, far more numerous than what we see from our pale blue dot. Not all planets form in calm, orderly environments. Many arise under conditions that would have seemed impossible before we began observing them. Some circle pairs or trios of stars. Others orbit pulsars, the spinning remnants of supernovae. Some appear in metal poor regions where planet formation was thought unlikely. Nature, it turns out, is far more inventive than any early model predicted. Wherever matter exists, gravity begins its quiet work, pulling dust and rock into worlds even in the aftermath of cosmic chaos in crowded nurseries or around faint volatile stars. Some of the youngest planets we've observed orbit stars barely a few million years old, cosmic infants still swaddled in gas and dust. Within these swirling disks, dust grains stick together, forming clumps that grow into rocks and eventually planets. Some glow with residual heat from formation, while others continue to accrete material, growing day by day. Their orbits shift, their atmospheres are still taking shape, yet they are real worlds in progress, forming in real time under the light of a newborn sun. These observations remind us that planet formation is not a static theory, but an ongoing cosmic process happening before our eyes. At the same time, some planetary systems we detect are older than Earth itself, silent witnesses to billions of years of galactic history, enduring long after their stars first ignited. Earth formed about 4.5 billion years ago, but some planetary systems we've discovered are far older, dating back 10 or even 11 billion years. These ancient worlds have been orbiting their stars long before our sun existed, enduring galactic collisions, stellar outbursts, and countless orbits without being destroyed. One example is Kepler 444, which hosts 5 small rocky planets. Its star is more than twice the age of the Sun, yet the planets remain tracing steady paths through time. These systems are cosmic time capsules, relics from the early universe when heavy elements were scarce. They may hold clues about the first planets ever formed, and perhaps even the potential for life billions of years older than anything on Earth. In a galaxy of such ancient worlds, we are the newcomers. At the other extreme, some exoplanets are unimaginably massive, tens of times the size of Jupiter. These giants challenge our definitions, sitting between true planets and brown dwarfs too small to ignite as stars, yet far larger than typical planets. Often found in distant orbits, they glow faintly from leftover heat and may have cores denser than anything we know. Some are mostly hydrogen and helium, with atmospheres thousands of miles thick. Their gravity would dominate moons and rings, shaping colossal weather systems across entire hemispheres. These supermassive worlds are rare, slow burning titans of the galaxy, unique objects that defy easy classification. Meanwhile, other exoplanets are extreme in the opposite sense, incredibly dense, small worlds where gravity squeezes the interior to unimaginable pressures. Some rocky planets may be twice as dense as Earth, with iron cores compressed into exotic forms. Their surfaces might appear familiar, cratered, mountainous, but stepping onto one would feel alien, the ground beneath unnervingly heavy. And yet some planets are almost the opposite, vast, lightweight, and puffed up gas giants. Their enormous diameters belie their low mass, making them tenuous enough that theoretically they could float in water. These fluffy worlds have atmospheres stretched and inflated by stellar heat, sometimes forming visible trails of escaping gas. They demonstrate how elastic and diverse planets can be, from the crushingly compact to the impossibly diffuse. One well known example in our own solar system is Saturn, the least dense planet we know. But some exoplanets take this to extremes. With densities lower than wood, these puffy worlds are almost entirely gas. In theory, they could float if placed in a large enough ocean. Many orbit close to their stars, where intense heat inflates their atmospheres. Beneath these extended skies, small dense cores may hide. Their clouds are sparse, their winds gentle, and their enormous shapes seem fragile, more like drifting bubbles than solid spheres. Gravity and heat hold them together, but only barely. At the other end of the spectrum, some planets have lost their atmospheres entirely. A planet's air is delicate, and over billions of years, it can be stripped away by stellar winds, radiation, or repeated impacts. Small rocky worlds near their stars may have once been shrouded in thick skies, only to end up as barren, lifeless surfaces. Spectral data from some exoplanets shows little to no absorption, hinting at stripped down planetary ghosts. Exposed rock, cratered plains, and perhaps faint traces of past atmospheres remain silent reminders that even planets are subject to the slow erosion of time. Meanwhile, some planets are still actively building themselves from the surrounding disk of gas and dust. Planetary formation can stretch on for millions of years after a star is born. Young planets continue to gather material, pulling in gas rock and dust from their protoplanetary disks. Infrared observations reveal hot, glowing clumps, gaps carved by gravity, and spiral patterns, all signs of worlds still in progress. These baby planets are unfinished, turbulent, hot, and unstable, with surfaces still forming and atmospheres thick and chaotic. Witnessing this is like seeing the universe sculpt a new world in real time. Destruction is part of the story, too. In some cases, planets vanish before our eyes. Kepler observed candidates that flickered and dimmed as they were gradually eroded by their stars, leaving behind dusty tails like cosmic comets. In other systems, collisions between planetary bodies produced sudden flares of infrared light, marking cataclysmic endings. Creation and destruction unfold side by side. Across the cosmos, worlds are born, shaped, and sometimes erased, all within the silent, ongoing machinery of the universe. Some exoplanets might be blanketed in metallic snow. On Earth, snow is soft, white, and familiar, but on certain hot gas giants, snow could be made of something entirely alien. Metals like titanium or iron can exist as vapor high in the atmosphere, condensing into droplets as they cool. Under the right conditions, these droplets might solidify and fall as glittering shards or crystals heavy and bright under foreign suns. On other planets, compounds like aluminum oxide could form high altitude clouds, producing mineral snow reminiscent of sapphire dust. Often these flakes never reach the surface, vaporizing mid descent, drifting silently in the upper skies. Strange weather shaped not by water, but by heat pressure and elemental chemistry. Some exoplanets are locked in intricate gravitational dances. In certain systems, planets move in precise interlocking rhythms, known as mean motion resonances. One planet may orbit twice for every 3 orbits of a neighbor. These patterns are not coincidental. They arise from long term gravitational interactions that stabilize the system and prevent collisions. In TRAPPIST 1, 7 rocky planets orbit a small star in such harmony, forming a cosmic clockwork where each world keeps pace with the others. These elegant dances can persist for billions of years, their balance quietly maintained in the silence of space. Yet not all systems are stable. Some appear precarious with orbits that stretch, tilt, or tug at one another over time. Simulations suggest that in tens or hundreds of millions of years, planets could be ejected, collide, or spiral into their stars. What we observe today may be only a fleeting moment in a system slowly unraveling, a fragile arrangement maintained for now, but vulnerable to change. Even massive silent planets are not immune to disruption. Some exoplanets follow extremely tilted orbits. While most planets lie near the same orbital plane, some exoplanets orbit at steep angles wildly off axis from their system's main plane. These unusual tilts hint at violent pasts, collisions, gravitational encounters, or migrations that knock them off their original paths. The universe is full of such exceptions, worlds that defy expectations, and remind us that even planetary systems, vast and stable seeming, are subject to chaos and upheaval. In extreme cases, some exoplanets follow orbits sharply tilted relative to their star's equator, even circling nearly perpendicular to it. Such dramatic angles often result from gravitational nudges by neighboring planets, close stellar flybys, or ancient collisions. Many planets may have formed normally only to be sent off course later by violent interactions. These tilted orbits influence climate seasons and long term stability. They also act as clues, telling us that a planet's history is rarely simple. Its path has been shifted, disrupted, and rewritten by forces beyond its control. Some planets rotate in reverse relative to their orbital motion, while most worlds spin in the same direction as they orbit. A few exoplanets are retrograde, turning the opposite way. This unusual spin likely arises from massive collisions, tidal forces, or strong gravitational encounters. The result is a planet whose days run backward, whose storms swirl counterintuitively, and whose sunrises and sunsets occur in reverse. Standing on such a world, the sky would feel subtly alien, with time and motion defying expectation. These rebellious worlds challenge our notions of planetary normality. Even without direct observation, we can measure the winds sweeping across these distant worlds, and they can be staggering. On some gas giants, winds exceed 500 miles per hour, fast enough to cross continents in under an hour. These jet streams are driven by extreme temperature differences, especially on tidally locked planets, where one side bakes under perpetual sunlight while the other freezes in darkness. Equatorial currents can carry heat around the globe, and storms may circle endlessly. We perceive these invisible gusts only through subtle shifts in starlight, a faint whisper of weather across light years. Some exoplanets face relentless bombardment from stellar flares. Not all stars shine gently, particularly young red dwarfs, which erupt with powerful bursts of radiation thousands of times stronger than the sun's strongest flares. Planets orbiting close to these tempestuous stars are constantly exposed, their atmospheres pummeled by ultraviolet and X ray radiation. Life. If it exists, there would need to survive extreme storms, and the surfaces of these planets could be continuously reshaped by radiation erosion or chemistry driven by stellar fury. If exoplanets have strong magnetic fields, they may be shielded from their stars' violent flares. Without such protection, their atmospheres can be stripped away molecule by molecule. Stars like Proxima Centauri remind us how extreme this can be. Intense bursts of radiation batter nearby planets, raising questions about habitability. Could life persist under such relentless energy? Could the air recover? Or would the surface remain scarred forever by a sun too young and tempestuous? On these worlds, survival depends not just on distance from the star, but on stability, protection, and the star's temperament. Not all red dwarfs are wild. Some are calm, stable, and slow burning, emitting gentle light for trillions of years. Around such stars, planets can orbit closely enough to receive warmth without suffering flares. Even tidally locked worlds, forever dividing day from night, may have regions of gentle climate along the twilight zone where light and dark meet. Here life could evolve uninterrupted for billions of years, sheltered beneath the steady glow of a peaceful ruby-hued sun. Some planets are adorned with auroras that blaze perpetually. Unlike Earth's fleeting northern lights, auroras on exoplanets can stretch across hemispheres, ring the planet, or even glow along the equator. Tidally locked planets could have day sides bathed in starlight, while night sides shimmer with constant auroral fire. Gas giants with massive magnetic fields might display auroras visible from space arcs of green, blue, or purple dancing across clouds. These skies are alive, charged with energy painting worlds in motion and light. On the hottest exoplanets, the atmosphere itself can be extreme enough to vaporize rock. Silicates aluminum oxide and other minerals rise as gas condense into clouds and fall as suspended particles, forming strange metallic skies. Spectroscopy reveals absorption and scattering patterns unlike anything on Earth. These mineral clouds can create shimmering hazes, metallic storms, or skies colored yellow gray or deep red. Supersonic winds may carry sand like dust across the atmosphere, sculpting surfaces from above. These worlds are harsh, dynamic, and surreal, where the very elements we consider solid become part of an alien weather system. On these worlds, clouds are not soft or familiar. They form from heat and gravity, turning solid rock into mist that drifts high above the surface. The sky itself becomes alien, made not of water, but of vaporized minerals suspended in the atmosphere by extreme conditions. Some planets are gradually spiraling inward toward their stars. Orbits can decay under the pull of gravity, and tidal force is slowly shrinking over millions of years. The planets appear normal. From afar, their days pass. Their skies shine, but silently. They edge closer to a fiery end. Signs of this process have been observed as orbital periods shorten by tiny fractions of a second, year by year. Eventually, these worlds may be swallowed by the stars that once gave them warmth, a slow, inevitable descent. Others take the opposite path, flung outward into interstellar space. Early gravitational interactions, particularly with giant planets, can eject a planet entirely from its system. These rogue worlds drift alone through the galaxy, free of stars, dark, cold, and nearly invisible. Yet some may retain internal heat or hidden oceans warmed by radioactive decay, harboring quiet, hidden activity. They are solitary wanderers, carrying secrets across the void unbound, but still very much planets. Some exoplanets follow orbits so vast they span entire star systems. These distant planets move in long elliptical paths, sometimes taking centuries or millennia to complete a single revolution. At their farthest point, they barely cling to their star's gravity. At closest approach, they speed past in brilliant heated flashes. Such extreme orbits may be the result of past planetary migrations or violent encounters scattering worlds into wide, sweeping trajectories. In a few cases, planets have been spotted hundreds of astronomical units away, their stars reduced to faint specks in alien skies, highlighting the staggering diversity of planetary motion across the galaxy. Some exoplanets may host weather so extreme it redefines the very idea of climate. On worlds scorched by close proximity to their stars, supersonic winds could sweep across the surface at thousands of miles per hour, carrying vaporized metals that condense into clouds or rain before hitting the ground. On icy planets far from their suns, blizzards of frozen methane, nitrogen, or ammonia might sculpt endless plains into dunes, ridges, or crystalline forests that shift over millennia. On other planets, violent electrical storms could ignite clouds of molten rock or metal, producing lightning that strikes again and again, reshaping landscapes in fire and fury. Yet, even among such extremes, there may be zones of calm. Tidally locked planets, with one face eternally toward their star, can have narrow twilight bands where temperatures or moderate winds are gentler and conditions might allow life to survive. These rings of perpetual dusk are oases amid violent climates, a delicate balance of heat and shadow where oceans might persist, or life could find a foothold in caves under ice or beneath volcanic vents. The diversity of weather across these distant worlds reminds us how varied planetary conditions can be. Some planets have oceans, some are completely dry, some are wrapped in metallic clouds, others in thick mists of exotic ice. Some experience seasons that span centuries, while others know neither day nor night. Each planet is its own experiment in chemistry, physics, and the interplay of energy and gravity. In observing these extremes, we learn not just about planets, but about the possibilities for life itself. Life, if it exists, may adapt to environments unimaginable, To us, surviving in boiling seas of acid, thriving beneath layers of ice, hotter than Earth's surface, or drifting in clouds of vaporized rock. Every exoplanet is a story, a natural laboratory of cosmic invention, showing that the universe is far more inventive and diverse than anything we have known. We are just beginning to glimpse the full spectrum of these alien worlds, planets, bathed in gentle starlight worlds, racked by eternal storms, rogue wanderers adrift in the void. And with each discovery, our understanding of what a planet can be and what life might endure grows deeper. These chaotic worlds live fast and dangerous lives. Their days may be brief, or their years cut short by close encounters with other stars. Orbits elongate, tilt, and twist, sometimes sending planets plunging toward their suns or flinging them outward into the void. In such systems, planets are dancers in a cosmic ballet of chance, pulled and pushed by invisible forces, always at the mercy of gravity's whim. Yet, even amid chaos, planets endure. Some cling to their stars, despite violent interactions, maintaining a precarious orbit that allows for fleeting stability. Others are cast out entirely, becoming rogue planets, lonely wanderers, drifting through interstellar space, cold, dark, and silent. They may never see the warmth of a sun, but internal heat from radioactive decay or residual formation energy could keep subsurface oceans alive, hidden beneath frozen crusts. These are worlds of extremes, where life, if it exists, would have to adapt to unimaginable isolation and scarcity. In crowded star clusters, planets might orbit in harmony, despite the chaos locked in resonances that preserve their dance. But in the galactic suburbs, far from the bustle of spiral arms, planets move slowly, almost imperceptibly. Their stars are ancient quiet and unchanging, offering long stretches of stability. Here, extreme storms are rare, flares are weak, and orbital paths are serene. Time stretches differently. Planets here may harbor environments that change over billions of years, rather than days or centuries giving life, if it arises the luxury of patience. Across the galaxy, from violent flare battered orbits to icy silent havens, planets are endlessly varied. Each is shaped by its environment, by the warmth or fury of its star, by collisions and close encounters, by the chemistry of its atmosphere, by the spin of its axis and the tilt of its orbit. Some are alive with storms auroras or subsurface oceans. Others are barren, drifting alone, scarred by radiation or stripped of atmosphere. Some may be entirely alien to our imagination, while others could mirror young Earth, a glimpse into our own distant past. The more we discover, the more we realize that the universe is a vast laboratory of planetary possibilities. From frozen giants coated in exotic ices to molten worlds with mineral rain from quiet ancient planets in the galactic outskirts to chaotic wanderers in crowded starfields. Each exoplanet is a testament to the richness and resilience of planetary formation. And as we continue to explore, we are not just cataloging planets, we are uncovering the infinite ways in which worlds can exist, survive, and perhaps, just perhaps, host life. Some exoplanets may have layers of clouds unlike anything on Earth, thick sheets of ammonia methane, or sulfuric acid drifting in dense churning skies. On others, the air itself may shimmer with metallic vapors, the remnants of extreme heat lifting iron or titanium into gaseous form. Storms can rage for centuries, powered by fierce winds and relentless temperature differences. Lightning might crack through mineral clouds, and auroras could burn across the poles with a permanent eerie glow. In these alien atmospheres, day and night may be distorted, shifted by slow rotation or tidal locking, creating worlds where time feels stretched, compressed, or disjointed. Some planets may even change their chemistry over time, gradually losing hydrogen to space or accumulating exotic elements from stellar flares. Others could be caught in a delicate balance, their atmospheres teetering on the edge of collapse, where one strong flare or collision could strip them bare. These are worlds in flux, living, breathing laboratories of physics and chemistry on scales we can barely imagine. And yet, despite the extremes, some of these planets may host pockets of stability. Beneath thick clouds and sheltered valleys, or within subsurface oceans, conditions might allow for slow, steady processes to unfold, chemical reactions, cycles of ice and water, or even the faint beginnings of life. Exoplanets remind us that habitability is not a single line on a graph, but a spectrum, a complex interplay of heat, light chemistry, and gravity. Across the galaxy, planets tell stories of survival, adaptation, and resilience. They endure supernova blasts, star collapses, gravitational upheavals, and radiation storms. Some are youthful and volatile, still forming from dust and gas. Others are ancient, silent witnesses to billions of years of galactic history. Each one, whether puffy, dense, frozen, molten, or spiraling through interstellar space, is a testament to the astonishing variety of worlds that exist and the myriad ways planets can persist against unimaginable odds. Some exoplanets may be covered in reflective clouds or ice so bright that they shine like distant lanterns in the darkness of space. High albedo surfaces, ice plains, salt flats, or metallic clouds can bounce stellar light back into space, making the planet gleam against the backdrop of its star. From afar, these worlds might look like cosmic beacons, glimmering silently as they orbit. The reflected light could fluctuate with the planet's rotation, cloud movement, or seasonal changes, creating patterns that telescopes might one day detect as flickering signals from light years away. Others could be dim, shrouded in soot haze or thick volcanic ash. These worlds swallow the light of their stars, casting long shadows across barren surfaces. Their skies might be eternally muted, heavy with aerosols, or layered with chemical smog that turns daylight into twilight. The planet glows faintly in the infrared warmth from internal heat, but invisible to the naked eye from afar. Some planets might alternate between these extremes. A world could cycle between brilliant reflection and muted darkness shaped by active volcanism, atmospheric changes, or seasonal shifts. Imagine a planet where one side gleams like silver under intense sunlight, while the other is cloaked in endless swirling dust storms. In all these ways, exoplanets teach us that worlds can be dazzling or forbidding, subtle or extreme, calm, or tempestuous. They stretch our imagination, showing that planets are not merely points of rock or gas, they are complex, dynamic, and astonishingly diverse. Some may be hostile to life as we know it. Others might harbor conditions where life could adapt in forms beyond our current understanding. With these new telescopes, we will begin to see exoplanets as they truly are, dots of color and light, sometimes gleaming, sometimes muted, each with its own personality. Spectroscopy will reveal their chemical makeup, hinting at clouds' oceans or exotic atmospheric gases. Some may glow with metallic clouds or shimmer with reflective ice. Others may be cloaked in haze, their surfaces hidden from view. Direct imaging will let us watch weather patterns unfold, see storms spiral across distant skies, and perhaps detect the glint of sunlight off liquid surfaces. We might catch auroras dancing across magnetic poles or witness the faint heat of volcanic eruptions. Over time, repeated observations could even allow us to map rotation seasons or changes in climate. These observations will transform exoplanets from abstract points into tangible worlds. They will no longer exist only in spectra or transit curves. They will become places we can imagine standing on, walking across, or simply watching as they turn slowly beneath the alien suns. Each new image will be a window into possibilities: temperate skies, frozen deserts, oceans of methane, clouds of metal storms that last centuries, or silent eternal nights. As our technology advances, the gap between Earth and these distant worlds will shrink. The unknown will become known, the unimaginable will become visible, and the universe will reveal its astonishing variety of worlds. In studying them, we learn not just about planets far away, but about the very nature of worlds themselves, how they form, survive, adapt, and sometimes even harbor life in the most unexpected corners of the cosmos. Soon, exoplanets will no longer be just shadows or faint signals. They will become places seen with our own eyes. Already, astronomers have begun capturing direct images of a few giant gas planets orbiting far from their stars. These images are crude, blurry specks of light, faint and small, but they are real. They reveal the glow of heat from planets still cooling after formation and track their slow orbits over years. The HR 8799 system, for example, gave humanity the first glimpse of worlds beyond our solar system, a historic moment marking a new chapter in astronomy. As instruments improve, we may one day see weather systems, oceans, or even signs of life. For now, these blurry dots are whispers of worlds, beginnings of a journey to understand them. The search for life often starts with these exoplanets. We look for worlds in the habitable zone, scan atmospheres for oxygen, methane, or other biosignatures, and study orbits' temperatures and host stars. Every detection sparks questions. Could water exist here? Could microbes survive? Could life in some form flourish? Even the smallest hint, a spectral wobble, or a faint absorption line, reverberates through the scientific community, for if life exists elsewhere, it will likely be on a planet quietly turning for billions of years, previously unnoticed. Exoplanets are our mirrors, our windows into the possibilities of life beyond Earth and the stories the universe is quietly telling. Every discovery challenges our expectations. We anticipated Earth like worlds, but instead found lava worlds, icy wanderers, planets orbiting dead stars, and worlds with molten skies or exotic rings. Some systems are packed with dozens of tightly orbiting planets, while others host rogue wanderers drifting through space alone. Weather chemistry and gravity interact in ways that defy our imagination, creating planets that are strange, beautiful, and diverse. The universe isn't just vast, it's inventive. The few thousand exoplanets we've found are likely only a tiny fraction of what exists. Yet they reveal a cosmos brimming with creativity, surprises, and endless possibilities. By exploring these distant worlds, we expand our imagination, confront the unexpected, and rediscover wonder. Exoplanets are more than scientific objects. They are invitations to dream, to imagine life in forms we cannot yet fathom, and to realize that the universe is not simple, but infinitely rich and astonishingly inventive. Each new planet we find is a story, a mystery, and a reminder that our understanding of the cosmos is just beginning. They may be more planets than stars in the Milky Way. For centuries, we imagined planets as rare, small companions circling here and there, solitary and uncommon. Today, the evidence tells a different story. Planets are everywhere. The average star in our galaxy likely hosts at least one planet, and many have several. That means there could be more planets in the Milky Way than stars, hundreds of billions of worlds, each following its own path. Some are enormous gas giants, others tiny rocky spheres. Some are blistering hot, others are frozen in perpetual night. Many defy all we thought possible, yet the numbers suggest something remarkable. Planetary systems are not special exceptions. They are the norm. The galaxy is not just a field of stars. It is a vast garden of worlds, each a quiet possibility. Among those billions of planets, some may be blue, some may breathe, some may be waiting. Somewhere out there, a planet like Earth may exist. We do not know where. We do not know what it looks like, but the odds are with us. Somewhere among the countless stars and their countless planets, there are surely worlds rocky, warm, wet, and alive. They may orbit small red suns or bright yellow stars. They may host oceans and forests or life so different we cannot yet recognize it. Perhaps they are quiet, just beginning. Perhaps they are ancient, with civilizations that rose and fell while Earth itself was still molten. We have not found it yet, but we are looking. Every telescope, every mission, every exoplanet discovered brings us closer. And when we finally find that world, our small distant twin, it will change everything. It will remind us that we are not alone in the vast silent dark, that other Earths exist, and that the universe is, after all, a play is meant to be shared. Our journey through the cosmos now draws to a close. Tonight we wandered far beyond the warmth of our sun, past familiar skies, into a galaxy filled with silent planets. Each world, a quiet answer to the question, what else might be out there? We drifted through dust storms and molten skies, over oceans locked beneath ice, and through atmospheres of metal wind or clouds. We watched stars flare and fade, planets flung into the dark, and imagined life, strange, fragile, impossible, taking root on worlds we may never touch. And throughout it all, one thought remains. The universe is not only vast, but full of places, with gravity and weather, with histories and futures, with stories still unfolding in silence. Each exoplanet we explored, whether real, theorized, or glimpsed faintly, is a world unto itself, a small gravity well, in a sea of starlight, a question wrapped in quiet, waiting for us to notice. And perhaps that is the wonder of it all, even as you lie here still and safe. The cosmos continues moving, spinning, and quietly creating countless new worlds, each with its own story to tell. Stars are shining, planets are turning, and somewhere in a distant sky, a world not unlike our own may be spinning slowly through its night. So if your eyes are growing heavy, if your breath has found its rhythm, if your thoughts drift like stardust in the dark, there is no need to return. You are already part of this universe, already floating, already home. Thank you for sharing this moment, this quiet voyage among distant worlds. If it has helped you rest, know that you are always welcome to return, to listen again, to dream again, to keep wondering. And if you happen to still be awake, you can move on to the next video. There are always more wonders waiting, more science, more stillness, more stars. But for now, rest. The planets will keep turning. The universe will wait. Good night.